All right, let's learn about how to interpret position versus time graphs. To be honest, this is a pretty important skill in AP Physics because the AP test writers often present you with information about an object's motion by presenting you with a position versus time graph. So let's see if I can get over my lagginess here, waiting for it to lag. There we go. So when I look at a position versus time graph, always the x-axis is going to be time, and that time is usually going to be presented to me in seconds. And the y-axis is going to be position, which is usually in meters, but I've got to be careful. Sometimes it's kilometers or some other unit, but always this is going to be where the object is, and this is when it was there. Now, one thing that's a little bit troubling is that position is often referred to in physics as x. So the y-axis is telling me the x position of the object. This is a little bit of a tricky thing to keep in mind here. All right, so let's just take a look at what we do with this here. All right, so let's just say that I have a car that starts off 30 meters to the observer's left and ends up 20 meters to the observer's right. So unless we have reason to do otherwise, we're going to go with the convention that says right direction is the positive direction and left is the negative direction. Sorry to all you left-handed people out there. We could do the same thing with east versus west, east being positive, west being negative, or up being positive and down being negative. Now, this is just telling me where it is at a given moment in time. So at the initial time, when I first started looking at what we call time equals t equals 0, it was 30 meters to the person's left. So I'm going to plot that on this graph at negative 30. The negative value means negative direction, 30 meters away from the observer. And then 2 seconds later, it was 20 meters to the left of the observer. And then 2 seconds later, at time t equals 4 seconds, it was 10 meters to the left of the observer. And at time t equals 6 seconds, it was directly in front of the observer, not to the left or not to the right. So the position would be then 0, not to the left or not to the right. 2 seconds later, then it's 10 meters to the right, and then it's 10 meters to the left. So these values are telling me where it is at given points in time. The slope of the line is the most important thing about this, though. All right, so that's the main thing I want us to get our heads wrapped around here. So the slope of the line is simply going to be the change in y over the change in x. That's always what the slope of the line means, right? But what's a little bit tricky here is the y value is position, which in physics we use the symbol x to represent, right? So basically, the change in position is going to be delta x over delta t. Well, delta x over delta t, that's what velocity is. So this slope of this line is telling me the velocity of the object. So on a position versus time graph, this slope is how fast that object is going. All right, so remember, velocity is the change in position over change in time. Well, this is a position versus time graph, so its slope is telling me that velocity. Now, keep in mind that delta means final minus initial. It's really important that you keep that in mind. It's not initial minus final, it's final minus initial. So I can basically take any points on here and use them to determine the slope of this line and hence its velocity. So let's just start off using a pretty obvious start point. So we're going to say, look, what's its final position? Well, its final position was positive 20. What was its initial position? Its initial position was negative 30. So final 20 minus initial negative 30. Well, that's going to give me 50 divided by the change in time, which was 10 minus 0. I get 5 meters per second. And here's an important thing to keep in mind with any kind of motion graph. And we're not just going to look at position graphs. We're going to look at velocity graphs and acceleration graphs. Just remember that the velocity is y over x, changing y over changing x. So look at the units, and we'll tell you what you're basically measuring. I've got meters over seconds. Well, that's what velocity is. So I look at this graph and I say, well, I know from these units, this slope has to tell me the velocity. Now, it's worth noting that I don't have to start at the endpoints. I could start it anywhere in here. So I don't always have to start at time t equals 0. So just to point out, I could have said, well, it was at position 10 at time t equals 8. And it was at position negative 20 at time t equals 2. So I could do the same thing here. I could say 10 minus negative 20 over 8 minus 2, and I'd still get the same slope because the slope didn't change. So you don't have to necessarily start at 0 and end at your most extreme one. You can take any point on here to make your slope determination. Now, big picture things here, though. The steeper the slope, the faster the object is moving. So when I look at these two, I can tell that the red one is moving faster than the blue one because it has a steeper slope. I can tell they're both moving in the positive direction, and they're both to the right of me. All right, so in this case, if I calculate the velocity of this one here, I'm going to say, let's see, I'll use this one here. I'll say 60 minus 10. That's the change in position. That's 50. And the change in time would be 10 minus 0, so it's moving 5 meters per second. Now, when I do this blue one, it's got a more gentle slope. It's not as steep, so that tells me it's going to be going slower. When I calculate this, I'm going to get a number that's less than 5. And in fact, the number I get is 2, because what I'm going to say is, I'm going to go, again, I'm going to go from 0 to 10 seconds because I got a nice intersection here. I don't have to interpolate. So I would basically say what I have then is final 60 minus initial 40 divided by 10 minus 0, and that gives me 2 meters per second. So it's, like I said, it's going to be a lower slope value. Now, another thing to keep in mind, a really important thing to keep in mind, is that the direction of the slope is the direction of motion, not where you are, but which way you're moving. So in this case here, I have a negative slope, so that tells me the object is moving in the negative direction. Here I have a positive slope, that tells me the object is moving in a positive direction. So I'll have a positive velocity here. I'll have a negative velocity here. Because remember, a negative velocity means you're moving in the negative direction. Now, keep in mind, this object here shown in blue is moving in the negative direction. It has a negative velocity, but it has a positive position throughout the time period we're looking. It was always to the right of me. That's what these values are telling me. This object was always to the left of me, but it's moving towards me. It's moving in the positive direction. Now, of these two, I can tell that this blue one is moving faster than the red one because it's got a steeper slope. It's a steeper negative slope, but it's still faster. It has a higher magnitude. It's just the direction is in the negative direction. So let's just try it here. So if I calculate the velocity for this one here, I'll say negative 30 minus negative 60 over 15 minus 0. It's moving in the positive direction at 2 meters per second. But when I calculate this one, I'm going to end up saying 20 minus 8. That's going to give me a negative 60. A negative 60 divided by 15 is going to give me negative 4 meters per second. So this one is going twice as fast, but it's moving in the negative direction. This one's going half as fast, and it's moving in the positive direction. What if the slope equals 0? Well, if the slope equals 0, it means the object is at rest. It is not moving. So in this case, the blue one is at rest 40 meters to my right. This one is at rest 60 meters to my left, or to the west, whatever other direction I choose to call it, positive or negative. All right, now let's look at this here, okay? So no one says that the slope is going to be constant. Slopes can change, right? We're going to start off today, and tomorrow just talking about constant motion, but we'll transition into changing motion. So let's just look at this here. So if I've got a straight line, that means I have a constant velocity. The velocity is not changing. Now, but what if, so in this one here, I see this object is moving at a constant speed, which I could calculate by taking the slope in the positive direction. It's got a positive velocity. What about this red one here? This red one starts off with a slope that's pretty close to 0. So I know it was probably at rest. It looks to me like this slope right at 0 was, at time 0, the slope was 0. It was at rest. But then it's going faster and faster in the negative direction. So I know that it's picking up speed and becoming more negative in its velocity. Now, if I look at this magenta one here, it starts off moving fairly quickly in the positive direction, but its slope is getting less and less steep. In fact, it reaches a slope of 0 at 7.5 seconds. So I know it momentarily stopped moving. It was at rest momentarily at time t equals 7.5 seconds, and then it began picking up speed in the negative direction. All right. And the last thing is what do the intercepts tell me? So the y-intercept tells me where the initial position, and then so I know this object started off at a position of negative 60 meters to my left. And I know that it passed by me at time t equals 10 seconds. So the x-intercept is a time value. So that tells me, oh, at time 10 seconds, it was 0 meters away from me. All right. And I think that's it for the screencast. Thanks for watching. Hopefully it wasn't too long. I'll check and see how long it took me.